we did some examples of, well, we did some more examples of the change of coordinate formula for changing coordinates in an integral. We looked at a triple integral, at a volume integral, how changing from Cartesian coordinates to spherical coordinates allowed you to evaluate the integral. So today we're coming on to the section on Green's theorem, which is the final section. In these multivariable calculus notes. And Green's theorem is a result which links together the two types of integrals we've been looking at for functions of two variables. Okay. So the two types of integrals we've been looking at, remember, are path integrals, integrating a linear differential form around a path in the xy domain. That's one type of integral. The other type of integral is a double integral, where you're integrating a function of two variables over a two-dimensional subregion of the xy domain. Green's theorem is a result which links these two. So let's have a look at the statement of it. Now, in order to read the statement of it, we need to have this terminology of what simply connected regions are. So that we looked at this definition briefly on Monday, but to discuss it, we can discuss it with the aid of these three diagrams down the right-hand side of page 35 there. So this diagram shows, in the three diagrams, shows some shaded subregions of the plane. Now the top one is what we would call a non-connected region, because the region is composed of two separate blobs. They aren't connected together. Okay? Okay, there's a lot of talk there. Thank you. So we have the distinction between connected regions and unconnected or disconnected regions. The figure in the middle figure there is a picture of a nice connected region. It's just a single blob, if you like. But we also have regions with holes in them, say, like this one here, figure 13 down at the bottom. So those we term, those are non-simply connected regions. So regions that have holes in them, like that, are termed non-simply connected. And one way of thinking about the difference between a simply connected region, such as the middle one, and a non-simply connected region, such as the bottom one, is to think of the boundary curve. The boundary curve of the simply connected region, the one in the middle, its boundary curve is just a simple closed loop with one component. Okay? Whereas the boundary curve of the region at the bottom is composed of two separate simple closed loops. Okay? So the boundary around the outside and then the boundary around the inner hole in the region. So simply connected regions, like the region in the middle there, this figure 12, are regions which don't have any holes in them, and so whose boundary is a simple closed curve. So let's have a look at the statement of Green's theorem, and we'll give a fairly, won't be a completely rigorous proof, but I'll give a fairly strong sketch of the proof, which has the main important ideas in it, and then we'll look at some applications of it. Okay. So Green's theorem is this equation here. It's relating two types of integrals. So the integral on the left here is the integral. We recognize that it's an integral over a curve C, and this C we know is a closed curve, and we can tell that by the addition to the integration symbol of that circle there. That circle in the middle of the integration sign simply signifies that the curve you're integrating over is a closed curve. Okay? So it's a curve whose start points and end points are the same point. Okay? Closed curve. And in addition, we have, well, C is the boundary of a simply connected region R. So C is going to be a simple closed curve, and inside it is going to be a simply connected region of the plane. And Green's theorem says that, well, if you integrate this linear differential form around the boundary C, we integrate pxy dx plus qxy dy around the boundary, we get the same result as integrating this difference of partial derivatives around, or integrating this difference of partial derivatives over the region R, which is contained inside the closed curve C. So in general, you've got some kind of simple closed curve C, and it's enclosing a region R inside it. So Green's theorem is relating the behavior of the linear differential form p dx plus q dy on the boundary C, how that behaves on the boundary, and integrating it, summing up its behavior on the boundary, with integrating that difference of partial derivatives across the interior interior of the region. Okay. It's quite an interesting result because it relates together the two different types of integrals. Before we go into the explanation of why it's true, there's just one interesting thing to pick out about it. You could ask, you see, the x and y seem to be treated differently here. We've got dq dx, but we've got minus dp dy. So why, I mean, in the original setup of the problem, we've got our x and y axes. There's no reason to prefer x over y, or there's nothing special about x compared to y. So why is it that we're looking at the difference of these two partial derivatives instead of the sum? So the x variable seems to be treated differently from the y variable in that one of them has a minus sign attached. But there's nothing too spooky going on. What really, it's the difference of these two quantities that's important. And the reason why the minus sign is attached to the y derivative there, what that's linked to is this choice for the orientation in the boundary curve. So remember, by default, when we say we integrate along a curve, a closed curve, the default direction is taken as being anti-clockwise. But there's nothing God-given about that. That's simply our choice to integrate around it in the anti-clockwise direction. If we were to integrate it around it in the clockwise direction, in the opposite direction, we'd be changing the sign of the integral. And so that would flip the minus sign over here on the right and make the minus sign be attached to the x and the positive sign attached to the y. Okay? So that difference, the way the x and y are treated there, is really just equivalent to our choice to say that the integral around the boundary, well, we're going to take that integral in the anti-clockwise direction. Okay? That's just our simple choice or convention. Equally well, we could go the other way around, and then the sign would be reversed here. Okay, so we want to think of how we might prove this. So sketch of the proof of Green's theorem. Now, it seems like it's not clear how to go about it because it's very general. Our region could be any kind of shape on our boundary, so there's a lot of generality to tackle. Okay? So first of all, we're going to prove it for a simple case. Now this is supposed to work for any simple closed curve in any shape of region. So, well, that's a bit too complex to tackle directly straight off the bat. So we want to tackle a simple case first. So what is a nice simple type of region to consider that has a kind of easily understood or easily handled boundary curve? Well, just like we did when we first did double integrals, the first regions we considered were simple rectangles. Rectangles which were aligned with the x and y axes. Okay? So we're going to consider a special case first where the boundary curve C is traversed anti-clockwise, is just this rectangle. It's the rectangle that's lined up with the x and y axis. And the region R is the region inside that. Now, to define the rectangle, we need a pair of x values and a pair of y values. Okay? So this rectangle is going from A to B on the x-axis and from C to D on the y-axis. What we're going to do is we're going to prove Green's theorem for simple regions like this, and then we're going to give a limiting argument that explains how we can use many different versions of this to cope with arbitrarily shaped regions. Okay? So first of all, we'll prove it for the rectangle. Okay? And we'll go about it by, we'll examine. So Green's theorem says these two integrals are equal. So what we'll do is examine both sides. We'll examine both sides of Green's theorem, both sides of that equation, and show that they're equal. Now, let's look at the left-hand side first. So the left-hand side is the integral over C, it's a closed curve integral, of p dx plus q dy. So p and q are two functions of x and y. We're integrating this linear differential form around C. Now, p and q are general. I don't know, p and q could be any two functions of x and y. So there's not much I can do. I can't use any facts about p and q necessarily. So the only way I can investigate this or simplify this as it's looking now is to make use of the fact that it's that the curve I'm going around is a rectangle. And rectangular curves should be, we can break down the behavior into the four straight lines that make up the rectangle. So to integrate around the curve C is to integrate around C1, integrate around C2, integrate around C3, and integrate around C4. P dx plus q dy in each one. Okay, so I'm just suppressing that. Make the equation simpler to write down. So you integrate around the curve C by first integrating along C1, then integrate along C2, C3, C4. But now, the behavior on C1, see, on C1, it's only the x variable that's changing. The y variable is held still. The y variable is held at the value c, and so dy is equal to 0. In C2, the x value is held fixed at b, so dx is 0. In C3, the y value is held constant at d, and so dy is 0. And in C4, finally, the last part of it, the x variable is held constant at a, and so dx is 0. Because of these conditions on these four straight line parts of the rectangle, this will simplify the linear differential form p dx plus q dy. So integrating along C1, I'm just going to be integrating from a to b with respect to x, because the dy part is equal to 0. So I'll just have p, it'll be p of x, but you see y is held constant at the value c. So the integral along C1 just reduces to this integral. Integrating a to b of p of x and c, because y is always equal to c along C1, and just integrating with respect to x. The integral along C2, well, there dx is 0, so I'm just integrating the q function. I'm integrating from c to d, and x is held constant at b, y is changing, and I'm integrating with respect to y. You can see how on each of the straight line parts, the p dx plus q dy simplifies to these various forms. So integrating along C3 is to integrate from b to a. Dy is equal to 0, so we're just integrating p at x, and y is held constant at d. And then the last part, integrating along C4, is to integrate from d to c. Because C4 begins at y equals d, it ends at y equals c. So integrate from d to c. The dx is 0, so I'm just integrating q, and x is held constant at a. I'm integrating with respect to y. So without knowing any further information about p and q, that's as much, sorry, that isn't an equal sign there. This is a, sorry, it's plus. There's four integrals. These These are these four integrals. Without knowing anything further than p and q, that's as far as I can bring this. I can't evaluate it anymore because I don't know what p and q are. So this is how the left-hand side seems to be behaving. And I've used the fact here that the boundary curve C is this simple rectangular path which is aligned with the x and y axis. So now I'll examine the right-hand side and show that it's exactly equal to this. Okay? So now examine the right-hand side. Well, what's the right-hand side? The right-hand side is equal to the double integral over R of dq dx minus dp dy. Dx dy. Again, I don't know what p and q are, so I can't use any facts about them. I'm just going to use properties of the fact that I'm integrating over this rectangle. So the first thing I'll do is I'll use the linearity of integration. So say this is the double integral over R of dq dx dx dy minus the double integral over R of dp dy. But this time I'll reverse the order of integration and I'll write that as dy dx. Okay, so I'm free to reverse the order of integration. But now I can actually make some progress with these two integrals now, because in the first one I'm into the inner integral, which is the integration that has to be performed first. There I'm integrating the derivative with respect to x, I'm integrating with respect to x. That'll just integrate to the function q. And here I'm integrating with respect to y the derivative, dp dy. So that'll just integrate back to the original function p. Well, to make it clear exactly what's going on, let's put in the limits of integration for each one. So this is dq dx, dx, and then dy. So this is this integral inside the other one. And here, well, x is the outer integral, and y is the inner integral. But now those inner integrals I can actually carry out now. So this is integral from c to d. And when you integrate the derivative of q with respect to x, integrated with respect to x, you get q of xy. But I need to evaluate that now. I've just integrated with respect to x, so that gets evaluated at x equals a and x equals b. And I still have the outer integral dy. And over here I get the same except working on p with respect to y. So you integrate the derivative of p with respect to y, integrate it with respect to y, you get back to the original function p. But that should be evaluated now at y equals c and y equals d. Now I can write down what this is. This is going to be q of by minus q of ay. That's how the substitution works. After you've performed an integral, you evaluate it at the top limit and subtract the evaluation at the bottom limit. Remember, you're evaluating at these x values. Then you've got a to b, and now you've got p of x d minus p of x c dx. Now this is some straightforward, some integrals with respect to y of q functions and some integrals with respect to x of p functions. But if you look above at what we ended up with as our final version of the left-hand side of Green's theorem, that's exactly what we have. Some integrals with respect to x of p functions and some integrals with respect to y of q functions. And all that's left to do to get this to look exactly like it was before is to split these integrals up using linearity and use the minus signs to flip the limits of integration. So I can write this as integral from c to d of q by dy, and it'll be minus the integral from c to d of q ay, but I can absorb the minus sign by interchanging the limits, This will be integral from d to c of q ay dy. And here I can absorb this minus sign by writing it as plus integral from b to a of pxd dx. And then these two minus signs cancel. Just give me plus integral a to b pxc dx. Now that should be exactly what we had for the left-hand side. Okay. Which is equal to the left-hand side Green's theorem we have above. So we've proved it in the case of a rectangle, simple rectangle like that, aligned with the x and y axis. By just kind of fully exploiting the fact that we were integrating over this rectangular region and integrating over the rectangular. And just noting that the first one, the left-hand side, integrating around the curve, because the four straight line pieces were lined up with the axes, it meant the linear differential form simplified a lot. And then integrating over the region, I knew what the limits were, a to b for x, c to d for y, and noting that the thing I was tasked with integrating, they were derivative with respect to x and derivative with respect to y. So I could perform one of the integrals, perform the inner integrals in both cases to get similar expression out. Okay, any queries about that or anything I could clarify on that? Okay, so it is possible to directly show the equality of those two integrals in the case of a rectangle. But rectangles are pretty simple. What about the general case? Now the general case, could be wild and wonderful. Any kind of oddly shaped region, and any, with its complicated boundary curve. Now here's where maybe my argument gets a little bit sketchy, but still essentially correct, and there's just technical details to deal with. But the way to think about it is, imagine this region approximated by rectangles, like we've just proved the theorem for. So imagine a load of lines parallel to the y-axis and a load of lines parallel to the x-axis. So we observe that we can approximate the region R using small rectangles. And we know Green's theorem is true over any one of these small rectangles. Of course, the approximation will break, the approximation will only really be at the boundary is where the errors will occur. Because at the boundary, rectangles can't fully give the curved boundary. So there'll be little bits of the region left off near the boundary, or maybe little bits, some of our rectangles might poke outside the actual region. So there'll be mistakes made at the boundary, for sure. And this approximation gets better. The approximation gets better when we decrease the radius, as we decrease the size of these rectangles. Let's just decrease the size of the rectangles. Okay, well that's kind of nice. But to do the integration over the whole region R, we have to integrate over all of these rectangles. Now I know Green's theorem is true on any particular one. But let's just look at a few of these rectangles drawn beside each other. Like this. So this is just some small part. Suppose it was like this. The point is, when you integrate over all of these anti-clockwise, something interesting happens. So you have to integrate around the boundaries of all of these little rectangles anti-clockwise. So we'll apply the special case to each rectangle. So special case of Green's theorem to each rectangle. And sum the results. So let's represent this, that the sum, I'll just kind of figuratively, sum over all the rectangles of the integral around the boundary of the rectangle. So this is your pdx plus qdy. This is equal to the sum over all the rectangles of performing the double integral over each rectangle of the dq dx minus dq dy. Dx dy. We're using summation sign in a strange way there. So on the left we've got adding up the integrals around the boundary of each rectangle, doing the left-hand side of Green's theorem. That's going to be the same as adding up the double integral over the interior of each rectangle, the difference of partial derivatives. So because we proved the special case, we know these two are equal. But, and it's clear on the right-hand side, we get an approximation to integrating over the full region R. Okay? And as our rectangles get smaller and smaller, the right-hand side will look more and more like the double integral over R, dq dx minus dp dy, dx dy. So this limiting process is as the size of the rectangles goes to 0. So this is a limit arrow. As the size of the rectangles approaches 0, this summation of all these double integrals over all the rectangles, this converges to the double integral over the region R. And we'll say a similar thing about the behavior of the left-hand side in the limit. But first of all, when you look at integrating over all the rectangular boundaries, see what happens when I come to integrate. When I'm integrating over this rectangle here, I integrate over its top edge from right to left. Okay, so I'm going anti-clockwise. So when I integrate over this rectangle here, on the top edge, I integrate from right to left. But when I integrate over its neighbor that's sitting above it, when I integrate around its boundary, I integrate over this same edge from left to right. So any of these interior edges, you integrate over them twice, because the interior edges are edges of two of the rectangles. But when you go around one triangle, you integrate along that edge one way. When you integrate over its neighbor, you integrate along the edge in the opposite direction. So those two will cancel out. So you're integrating the same thing. You're integrating pdx plus qdy. You're integrating over each interior edge, you're integrating over it twice. Once in one direction, once in the opposite direction. So those two are the negatives of each other. So when you add them all up here, they all cancel out. So the only things that survive, the only things that survive is this. I'm going to write this like a funny sum. I don't normally see summations written like this, but we're summing over all exterior edges of the integrals over each of these edges, p dx plus q dy. See, when I integrate over this collection of rectangles here, the only ones that survive are integrating around the exterior edges. Okay, all of the interior ones will have cancelled out. See, those edges. Those, what I've drawn here in solid lines are just the exterior edges. And what I've drawn in dotted lines are just the interior edges. So when you do the integrals around all these little rectangles, everything cancels out except the integrals around the exterior sides. And of course, in the limit, as the size of these rectangles approach 0, this converges to the integral around the boundary curve C of p dx plus q dy. So if these two are always equal, in their limits, well, that's where the technical details are, I guess, in showing that this equality is preserved in the limiting process. But in this limiting process, these two are going to be equal. So this result is Green's theorem. So on the right-hand side, you see integrating over all the little rectangles. That approximates the two-dimensional region R. Integrating around the boundaries of all the rectangles on the left-hand side. Well, most of the edges cancel out because you're integrating over each edge twice, once in one direction, and its neighbor goes in the opposite direction. But the only ones that survive, the only edges which are edges of only one rectangle are the ones on the outside, because they don't have a neighbor sitting beside it, because they're exterior edges. Okay? So this gives us our proof of Green's theorem. Okay? So we just need to deal with the technical issues, the technical details of this limiting argument. But we won't do that. We'll content ourselves with just that sketch here. But it is essentially correct, and that is the main method. So this limiting operation here, this is the same limiting process here as the size of the rectangles goes to 0. The rectangles decrease. Obviously, as you shrink the rectangles, you need more and more of them to do the approximation. So, okay, is there any questions about that kind of sketch of the proof? So we're able to prove it directly for these rectangles, and then using rectangles to approximate any area gets us the general result. Okay, so let's pick up, let's do an example of one of these. So this example here, example 1.23, well, this references example 1.22. So in example 1.22, we integrated a function. We integrated this linear differential form around the boundary, around this square. The square between 1 and 2 on the x and y axes. We integrated this 3x squared y squared dx plus 2xy dy. So around the boundary, we found this integral came to -18. So if we apply Green's theorem and perform the related integral over the interior of the rectangle, we should observe the same result. We should get minus 18 as well. So let's have a look at that now. Example 1.23. So from 1.22, we get the integral around the closed curve C of p dx plus q dy came out to be minus 18. So we'll expect the same answer for doing this integral here over the region. So gt implies that minus 18 is equal to the double integral over this square. And make sure those partial derivatives are right. So dq dx, so q is the function 2xy, so dq dx will be 2y, and then minus dp dy. So p is 3x squared y squared, so dp dy will be 6x squared y, and we're integrating dx dy. And we're going from what, this is the square between 1 and 2 on each axis, so it's this integral here we need to do. So we leave the outside integral alone, and we perform the inner integral with respect to x, so we get 2yx minus 2x cubed y. And this needs to be evaluated at the limits 1 and 2. Those are limits for the x variable. So when I evaluated at 2, I picked up 4y, and that's minus 2 times 8, so minus 16 y. Then I subtract the evaluation of 1, which gives me 2y minus 2y, which is 0. So it seems to be just integrating from 1 to 2, 4 minus 16 minus 12y dy. Kind of right. Okay, well that's nothing stopping me from doing that. You get minus 6y squared. Evaluate to that 1 and 2. So this comes out at minus 6 times 4, so minus 24 minus 6. Minus 24 plus 6, yeah, is indeed minus 18, as expected. Okay. So there, okay, just taking a rectangle, we can confirm it's true for this particular choice of P and Q. One interesting application of this, we'll finish with this for today. Please spend some time reading over the rest of that chapter. There's a few little things I haven't gone through exactly. Probably finish those off next week, in the lecture next week. But they're really just further applications of it. But one nice application to look at is this section here, 1.20. That's to think about, can we use Green's theorem to tell us about the area of a region? Well, now there's a few different ways to do this, but if we make this particular choice of P and Q here, so if we choose P, for the P function, if we just choose P of xy to be minus y, and Q of xy to just simply be x, and when we apply Green's theorem to this, we see that the integral of q dy plus p dx, applying Green's theorem, we see that it's twice the integral over R of dx dy. But this is integrating, see, dx dy is the area element. So this here, what we're seeing on the right-hand side, is 2 times the area of the region R. So if you divide both sides by a half, we get this expression here. that the area of any region can be found by integrating this linear differential form, x dy minus y dx, integrating that around the boundary of the region. And this is quite an important application, and an important mechanical application in the field of cartography. And there are devices called planimeters. So planimeters are devices that allow you to, they're generally used on a map. There's a nice picture to show you to do with forestry. Yeah, this one here. This is an example taken from forestry. So we've got a map here of a mountainside, and there's various plots marked out on it. So this might be something used by those planning forestry. Now, doing agriculture on flat ground is fairly easy. Most fields tend to be rectangular, so working out the areas of rectangular fields is a fairly straightforward business if it's plain flat ground. Of course, most forestry, or a lot of forestry in this place takes place, in this country takes place in hillier regions, in the mountainous regions. So the regions tend to be not, it's not so easy to lay out everything in rectangles. So the plots of land that you're planting trees in, you need to be able to work out the areas nicely from that. So here you've got a map and various plots of land marked out on the map, and what's sitting over the map is this mechanical device called a planimeter. Now this bottom disc of it is a fixed point. So it's got these two arms. So you fix a point still. That's just to give a fixed reference origin. And then you can see at the top there's a little bit of a magnifying glass at the top. But that disc at the top will have a crosshair in it. Will have a marked point in it. What you simply do is you maneuver the marked point around the boundary of the region. And then in the readout here, you can see there's various scales and dials in the place where those two arms come together. And as you move the thing around, the dials on the device move. And what it's registering is the area that you've enclosed inside the closed curve that you've drawn around the page on the map. Okay? And, well, these devices can work in various ways, but in a sense, you can understand that what they're implementing is this. What some of these are implementing is this kind of result from Green's theorem, that you can obtain the area of a region by performing a certain operation around the boundary of the region. Okay? It doesn't just have to be a simple, straightforward rectangle. Okay? And so what this device is doing with it's got its fixed point on the map, there's various gear, wheels, and levers in here. So as you manipulate the crosshairs in this site here around the boundary of the region, what's registered on the planimeter here is the area of the region that is enclosed. So it's got this very nice illustration or application in these cartographic devices. Okay, so I guess we'll leave it there for today.